Where we stand in this class. This is the last lecture for the semester. And what we are going to do is to quantify a little bit the modern, already not so modern, like for the last 50, 60 years, modern perspective of phase transitions, and specifically I'm going to talk about the Ising model. Ising model. Now, it's a rule of thumb, when you have something that is named after someone, usually this is not the someone who invented this thing. So the Ising model was actually invented by somebody called Lenz. 4 years, Ising was his student. He solved the problem erroneously. So the solution of the Ising model as provided by Ising is completely wrong. But the story is actually interesting because Ising turned to be an engineer eventually. Not exactly an engineer. He was taken by the Nazis to the Holocaust camps. And when he got out of it, the Ising model became extremely important and extremely famous. But he hasn't contributed since then anything, at least to physics. But the perspective of Ising model, well, actually more accurately by Lenz, on the how phase transitions occur is exactly how we understand the phase transitions nowadays. Now I remind you, the problem, we have a system with particles can be atoms, molecules, whatever, and the basic understanding that the magnetic moments or the magnetic spins of each of those particles are oriented completely randomly, right? And this is actually what happens for high enough temperatures for any system, right? If you heat it up, you will see that the magnetic moment goes to zero, magnetization is always broken. But what is observed in reality, you take such a system and you plot the total magnetic moment, which is what is the total magnetic moment, is a summation of mu si. I goes from 1 to n. Right? This is the total magnetic moment, and you plot, for example, the z value of this magnetic moment, or just the absolute value of this magnetic moment. It absolutely doesn't matter. What happens is that for high enough temperatures, largely, the magnetic moment is 0. You reach a critical point, Tc, Tq, and after this, you'll get either positive or either negative magnetic moment. So we're getting either here or here. So, and what we called it a spontaneous symmetry breaking, right? Why spontaneous? Because the only thing that we modified is the temperature. You can create magnetic moment by applying external field, and then there is a preference for all those particles, all those magnetic moments to lie in the direction of this magnetic field. Right? So this can happen, but what we see is that we do not apply any external magnetic field, H equals 0, still there is spontaneous magnetic moment, so somehow at least a macroscopic part of those particles prefer to point exactly at the same direction. Okay. All right, so in statistical physics, as you already probably noticed, is not that we try to take into account everything. Okay, so we can say, oh, there is such and such interactions and the particles have a specific lattice, etc., etc., etc. You cannot take anything into account. Why? Because the system is too complicated. Again, there are a huge number of particles. The interactions are very complicated between those particles. You try to catch the notion of what's going on inside by throwing away a lot of stuff and keeping only something that is important. So the idea of in the Ising model is as follows. So if you look on a specific spin, okay, if you look on the specific spin, then the following happens. So there is an interaction of the spin. Let's assume that this is SI. So there is an interaction of this spin with an external field. So the energy E for this specific spin, SI, is simply minus SI multiplied by H. And here we have some mu0 over here. Okay? What is H? H are external field. SI is the spin that I'm of this specific molecule or atom, and mu0 is some magneton quark. Okay, great. So this is a self energy due to external field. If there is no external field, there is no contribution to the energy. Great. Sorry. Next thing is the spin-spin interaction. Okay, so different particles interact with each other. Okay. And we can say that it is the interaction of SI with some other spin Sj, right? But of course, you have to count all, and there is some constant that defines the interactions. Usually it depends on I and it depends on J, all right? And it's also have a minus sign. Now, it's not enough to take a specific interaction of a given particle I with a given particle J. You have to count all the particles of J that you have inside your system. Okay? And the idea of Ising is as simple as that. So if you look on the energy of a given spin, it's the interaction with the external field and the interactions with all the different other particles that you have inside the system. Right? Now, of course, this Jij should somehow depend on the distance. So it's reasonable that two particles that sit nearby, they will somehow interact. But if the particles are really far away from each other, they won't feel, for example, due to screening that always occurs in such type of systems. So they won't interact at all. So usually you write this down as interaction of a particle at position R with particle at position R prime, okay, and J will be the dependent on the distance R minus R prime, the absolute value. Let me write it down a little bit larger. So this interaction should be, the coupling should be distance dependent. So R minus R prime, absolute value. Okay, so this is the idea. There is the energy of a given particle. The interactions with everybody else is produced due to spin-spin coupling, and you have to sum all the possible interactions. And well, this J of R should somehow converge to 0. Because it's, well, usually they do not feel each other for faraway distances. Great, yes?
What is screening?
So screening, for example, you have two particles, okay? Let's say about electric screening. So the two particles, if you have just two particles, according to the Coulomb law, they will always feel each other because the force goes as Q1, Q2 divided by the distance squared, okay? So you can say they always feeling each other. You can say, well, maybe this is extremely small, but the interaction, Coulomb interaction, always hold. Okay? But in a system where there are also other particles, other charges, the interaction of Coulomb law is actually not this, but multiplied by some e to the power minus r divided by lambda. Okay? So the interaction decays not as a parallel, but exponentially fast. This is the screening part. Okay? Why? Because there are many particles and they somehow affect each other, and when you count all of this, you will see an effective interaction between two particles in a system where there are many other particles that looks like that. Exponentials decay much faster than parallels, so for r larger than lambda, you actually don't see anything. But if I wouldn't have this screening part, I will always have something. Okay?
Okay.
So we assume that it decays fast enough. Okay? We assume it decays fast enough. Now, so what is going to be the total energy in such a system? Okay? So the energy is what? So you have to count all the different energies of all the different particles. Right? So it's E of SR, a summation of all possible R's. Right? But you have to be a little bit careful with that. So how you have to be careful? So first of all, you have this minus mu, all possible R's, SR, H. So this is the contribution due to interactions with the external field. Interaction with the field. Interaction with external field. And here you have minus, and I will plug 1/2, and a summation of all r's, summation of all r primes, and the 1/2 here just not to count everybody twice, right? Here it is the interaction part. It depends on the r minus r prime. Okay. And here I have sr dot sr prime. This is the spin-spin interaction. And unlike the interactions with the external field that goes away when h equals to 0, this guy always present. Okay? Because they're always particles. Each of those particles have some, or atoms, each of those atoms have a specific, or molecules have a specific spin. They're always present over there. So they have to interact with each other somehow. Okay? Okay, so this is the general idea of the Ising model, or let's call it as energy for the Ising model. Okay, so we are assuming that the number of molecules inside the system is constant. Okay? And we also assume that all those atoms are not moving away. Okay? So you can assume simply that the atoms or the particles sit on a lattice. So positions do not change as a function of time. Okay, so everything is static. The only thing that it's not static is the orientation of the spin. The spin can interact with each other. Different interactions or different energies create dynamics, so the spins can sometimes point upwards, sometimes to the left, sometimes to the right, sometimes in that direction, sometimes in this direction. Right? But the number of spins is something that is not modified as a function of time. Yes?
Is there a dot product between?
Yes, so when I have two vectors, it's of course a dot product over here and a dot product over there. Energy have to be scalar, right? Okay. Now, what always interests us, the interest is always in some thermodynamic quantity, and this thermodynamic quantity can be always derived from the free energy, and free energy always can be defined, but it's actually defined by the partition function. Okay, so the quantity that we want to compute is Z, which is summation over all states, okay? Summation over all states of e to the power minus b of energy of the system. Okay. Now sometimes it is written in slightly different form due to the quantum notation. So I can say that e to the power minus beta h is an operator, right? Now, when I write it down like this, it's the value of the operator Hamiltonian in a specific state n. So when I count over all states, I will just say that it is Z, it's a summation over n, all possible n's that I have inside my system, over this guy, right? So I can write it in a quantum notation. So instead of writing it like this, right, what is this? It's just the trace of the operator. This is trace of e to the power minus beta Hamiltonian. So sometimes instead of saying, oh, I'm performing a summation over all states, e to the power minus b e, and e have a specific values, I'm just writing it like this. It's exactly the same, but actually we don't care about quantum notation or quantum physics over here, because everything is some sort of a classical. The only quantum point over here is usually that SIs or SRs have a discrete values. All right? Okay. Now, this is the main object that we need to compute. We are operating with a constant number of particles, right? So, which ensemble, and we have a specific temperature. So, which ensemble we are?
Canonical.
Canonical ensemble. Okay. So, we are dealing with canonical ensemble for this system. We know what the energy is, right? So, the only thing is how we compute all those sums over here. The only trick that we know is factorization. We don't know any other tricks. And I can tell you that nobody else actually knows any other tricks. There's no other trick. There's just this factorization. So eventually we need somehow to factorize. So when I'm telling you nobody else knows any other tricks, it's not exactly true, because we know that somehow, maybe in the representation of the spins, it can be not factorizable, but if we stand on over our head and we'll extend our left arm up and our right hand down, somehow those particles, we can create out of them quasi-particles, and then we can factorize everything. So this is what we've done so far, all the way. Sometimes it was for the particles, sometimes it was for energetic states, but this is the only trick. You want to factorize, all right? So if it's not factorizable, you do it, something, create new particles, create new states, and there it's going to be factorizable. Now, why it's not factorizable? Okay, so remember, for factorization, this is our E. When I'm saying all the different states, SR, okay, SR can point in different directions. Can be discrete number of directions and can be continuous number of directions. Let's assume that SR can point only upwards or downwards. Okay? So we take SR, we have +1, and we have -1. Okay? As simple as that. Okay? So we have a lattice. On top of this lattice, there are part spins. Each spin can point either upwards or either downwards. Okay? Nothing else. why it's so difficult to compute this summation over all possible states when we have this specific energy. Okay. The problem is this self-interaction. So you remember, in order to factorize, two conditions have to apply. The energy have to be a sum of different entities. Well, yes, it's a sum of different entities. There is a summation over here. There is another summation over here. So our energy is just a summation over different entities. Those different entities, right, have to be independent. Okay. Here I sum over different SRs. Well, S1 is independent of S2, is independent of S3. I look on each different spin. I say you can point either upwards or downwards. Spin number 2 can point either upwards or downwards, and I cover all the spins and they are independent. Great. The problem is that the sum is not independent because of those guys. Right? Right? Those guys make the sum dependent. It's not just a sum. If I had a summation of S over R, SR multiplied by H, yeah, it's a sum over independent entities. But the moment I have here S1 multiplied by S2, for example, okay, it's not independent. The energetic state, each energetic state depends on the values of two different entities. So either I create something that effectively will be independent, or I don't really know what I have to do. Okay? So this interaction term, this is the main problem, because it won't allow me to factorize. Right? So the moment that I have a sum, I know, we have done it before, I know that a summation in the exponent leads to the multiplications of the different states in the partition function. Here, there is no such thing as independent summation, then therefore, it's over. So, what can we do? The first thing that we can do is just to describe to you that indeed, when I have no interactions, when I have absolutely no interactions, I can actually solve the problem. Okay, so, the first approximation is just to throw away the interaction term. Okay? So the first approximation that we will do is to assume that JRR, RR prime, equals to 0. So first, assume that J R minus R prime equals to 0. Okay. Then Z is a summation over all states e to the power minus beta, right? Multiplied by the energy. What is the energy? Minus mu 0 multiplied by summation over all R, SR, multiplied by H. Okay. This is a sum of independent entities, right? So I can say that it is Z1 multiplied by Z2 multiplied by Z3 multiplied by Z4 multiplied by Zn. N is the total number of particles that I have inside my system. Is the number of particles in the system. Why I can do that? Because the different values of the energetic state, there is no multiplication between S1 and S2 and S3 and S4 and S5. Okay.
Could you repeat what J means?
J is the interaction, spin-spin interaction. So it's the interactions between two different spins. Okay. So this also sometimes called free-icing. Free-icing. Or interaction free-icing model. All right. So what is Zi? Zi, I have to count over all states, but now not of all the different spins in my system, all states of SRI. And SRI can have +1 or -1. Let's do it. Z and Z. Right? We need a direction. So all states of SRI of what? Of e to the power minus beta, and we take out of this only the contribution of the state, not state, of the spin Ri. E to the power minus beta, and here we have minus mu0 SRI dot H. Now, since SRI have only two directions, right? Plus Z and minus Z. And we'll also assume, at least here, that H equals to H in the Z direction. Okay. So what we have, all states is just summing over two values of SRI. So it is e to the power minus minus, it's a plus, so it's beta mu0 H multiplied by 1 plus e to the power minus beta mu0 H multiplied by 1. That's it. Now I can write it down as what? As 2 hyperbolic cosine of beta mu0 H. So this is Z of I. Notice that the total Z in the interactions free-icing model is Z1, Z2, Z3, Z4. So it's independent of I. Meaning, for all I, Zi equals to 2 hyperbolic cosine of beta mu0 H. Great. So we threw away the interactions. Therefore, we know that Z equals to Z1 to the power n. And Z1, we know what it is. So Z equals to 2 hyperbolic cosine of beta mu0 H to the power n. Okay. Yes.
How can we know that the spin has only two discrete values here?
I am assuming that. Can I assume that?
Yeah.
If I have 4 different values, would it matter?
No, but
It's not going to be cosine. It's going to be some other function. But in a second you'll see that it actually doesn't matter.
indeed, when we but how do we know it has discrete values? I mean,
Oh,
when we
so
observe
this
it,
is
it does have discrete values.
So
but
you assume that
when we don't observe
you
it,
do know that spin have discrete values, right?
only when we observe it.
Well, in total, it have discrete values. What do you mean when you absorb it? Eventually, the spin have this value and this value and that value and that value. You don't know what the value is, but it defines different states.
Yes, but this is under a. I mean, it can be in the x-axis.
So let's assume it can be only in the z direction,
Oh, okay.
right? So the question is, do I need to actually include everything? Okay? And the answer is no, because I will show to you that even when I do not include everything, it still have a valuable result. And even I will include everything, but I won't include the interactions, the result is going to be exactly the same.
So now you want to calculate the average energy?
You don't need to, you don't want to calculate the average energy, right? Because what do you want to calculate?
F.
F is good, yes. So you can calculate F, which is 1 minus over beta log of Z. But what is the observable where you see something? It's M, right? What is M? The magnetization. So it's a summation I goes from 1 to N over what? I goes from 1 to N over SRI. Okay? And of course, it fluctuates because SRI are fluctuating. So we will see, let's take the average. This is the observable that people show to you. When I'm saying there is a phase transition, I'm plotting the magnetization as a function of temperature, and there is a transition. Okay? How do I compute the average M from whatever I have right now? So actually I don't need this Z in order to compute average M.
Because the spins for each particle are independent.
Yeah, but they're independent.
Interaction.
Yeah. So we call it M average. So the average of the sum is the sum of the average. The most important thing that you have to know always. It's summation I goes from 1 to N of SRI. Okay. Now, how I compute SRI? SRI is what? The average value of SRI. So it can have only two directions, either plus 1z, minus 1z. So it is plus, and you have mu 0 multiplied by z hat. Okay? More powerful. Sorry?
Why mu 0?
So the average, the spin, what I have here, because you have a magnetic moment mu 0. So I'll have mu 0 over here, and I don't have mu 0 over there. Right? So it is z multiplied by a probability of plus 1, and it's minus z or probability of f minus 1. Right? So what is the probability of f1? I know that z1 is produced out of this Boltzmann factor and that Boltzmann factor. So it is z multiplied by e to the power beta mu 0 h divided by 2 hyperbolic cosine of beta mu 0 h. And here I have minus z multiplied by e to the power minus beta mu 0 h divided by what? Divided by 2 hyperbolic cosine of beta mu 0 h. And I obtain that the average SI equals to what? To, so 1/2 hyperbolic tangents of, no, yep. Beta mu 0 h. So the average magnetic moment, it's mu 0 hyperbolic, all the different SRIs are exactly the same, so we can add it over here. That is n multiplied by mu 0 of SR1, right? So it's mu 0 multiplied by n multiplied by hyperbolic tangents of beta mu 0 h. Okay. This is the result of the magnetic moment for the interactions-free Ising model. Let's plot it. Now,
Stas, can I get it out of the Helmholtz free energy?
yeah, sure. But it's much more easier to do it that way. You've already seen this computation before. You can also get it out of here by taking the appropriate derivative. But you don't need to. When you have a summation, it's always easier to work on each particle independently because they are independent. Okay, so we plot the magnetization as a function of the temperature, and the most valuable part is that h equals to 0. So when h equals to 0, what is the value of hyperbolic tangents? 0. Okay. So hyperbolic tangents of 0 equals to 0. So we have such behavior. It's just 0, 0, 0, 0, 0, 0, and it's 0. It's always 0. So absolutely no phase transition. Should we expect this? Of course. We know that phase transitions occur due to some sort of interaction. And if we kick out all the interactions in the system, there should be absolutely no phase transitions. Each particle behaves on its own, okay, doing whatever it's doing, without caring about its neighbors and next near neighbors and next near neighbors. It doesn't care, right? So why should it depend on the temperature? It doesn't. Okay, so we have absolutely no average magnetic moment, and this is why the interactions-free Ising model is boring, extremely boring. But it's not exactly that boring because it gives us an idea about how to solve this problem, even approximately, when there are interactions. Okay. So no phase transitions for the interactions free. We have to include the interactions somehow. We don't know how to factorize it. Nobody really knows how to factorize it, at least for 3 dimensions. So we're going to a different approach, which is called the mean field theory. And what is this mean field theory? So, including interactions, mean field theory approach. The idea is as follows. So you have your system, the particles are somehow sitting on a specific lattice. You already know that. For each lattice point, there can be a spin. In our case, it can be either up or down, but it absolutely does not matter. There are different spins. Now, you look on this spin and you say the following. Let's look on this spin. So this spin, there is interactions. There are absolutely no external field. Let's assume that there is no external field. The spins see some specific area around it, and it feels it due to the interactions. And we can say that, well, somehow this field produces an effective average spin. We call it m. Now we can say, well, Why should it produce an average spin m, okay, of this specific spin? Because when you look on what we obtain, and just I will point out to you that we obtain that the average spin SI average was z multiplied by hyperbolic tangents of beta mu 0 h. Right? So it's only because we set h to 0, the average moment was 0. But this is the result that we obtain. Now let's assume that there are different spins around it. Okay? How they exactly oriented, I don't really know. Let's assume that they oriented somehow, that they produce an effective spin m. It can point upwards, it can point downwards, I don't really know. But there is an average spin due to the field, effective field, of all its neighbors, right, that produces this effective spin m. What I'm saying that due to interactions, the average spin is going to be m. Now, this spin is not so special. If we look on this guy, it seems, due to symmetry, almost the same surrounding. So the same surrounding effectively will produce the same average, m. And if you look on some other spin over here, it says also the same surrounding on average. And the same surrounding on average will produce an average spin m. Why? Because they create an effective field. The effective field, according to this guy, produces an effective spin, average effective spin. And this effective spin, this is the assumptions on this mean field, because it's mean that all this effective spin, called it field, and it's exactly the same, have the same average value everywhere inside our system. Is it absolutely true? Let's see for us in a second, okay? But the idea is that there is some m, I don't really know what this m is, but it's the same for all the different spins inside the system, okay? So we take this m into account and we work with it. I don't know what this m is, I just assume that there is some m inside the system. So what will happen if I'm assuming that there is an average spin m in the system? Now, this assumption leads to the following. The only problematic term that I have inside the system is SR dot SR prime, right? This is something that I neglected, that was inside the system before due to interactions. I threw away the interactions. Now I want to include it, and I want to use this assumption that there is some sort of an effective field m that is present inside the system. Okay. So what happens now? I can write this down in the following. So SR equals to m plus, how I write it? Plus SR minus m.
What is this now?
SR, so let's do it like this, and like this. Fine? You were worried about the...
No, it's equal to...
It's the same, right? So it's cancelled. So I haven't done here anything. I just added m and I subtracted m. Okay. I can do it the same as SR prime, which is going to be m plus SR prime minus m. Right? The same, absolutely no assumptions, this result is exact. Now let's multiply those two guys. SR dot SR prime, which is m plus SR minus m dot m plus SR prime minus m. Okay. I multiply those things. So I have m dot m. I have plus m dot SR prime minus M. I have plus SR minus M dot M. And I have SR minus M dot SR prime minus M. And here is the assumption, which is crucial. On average, each spin have this M. What exactly this M? I don't really know. Okay? But there are of course fluctuations. SR minus M are the fluctuations of each spin around its average. I'm assuming, and this is an assumption, so the fluctuations are small. Therefore, I can neglect this part. Okay? That's neglected. Why? Why not? Okay? It's the sometimes it's the physicist approach. I have some small terms. I can kick them out. Will it work? Well, we'll see later. Okay? Because I am assuming that the fluctuations around the mean value are small. I haven't proven to you. I won't prove it to you. I will just assume it.
Shouldn't be then minus M squared.
Sorry?
Shouldn't be
Just m squared? So let's assume, think about it the following. This is m squared. This is the correction, the first order corrections. This is the second order corrections. I'm getting rid of the second order corrections. Okay? I'm keeping only the first order. I'm not proving you that it's allowed, and it's actually not allowed sometimes, but it still works pretty well. Okay, so what happens now? If I got rid of this, so I have m squared. Here I have plus msr. I have minus m squared out of this guy. I have plus this was sr prime plus sr multiplied by m, and I have minus m squared. Okay, those are the fluctuations, and I got rid of them somehow. Okay, so overall, what I have minus m squared plus msr prime plus sr multiplied by m. Okay, so this is my assumption of what the multiplication of sr and sr prime. The prime, here's the right row. Now, I stick it inside the value of z. Z equals a summation over all states e to the power minus beta e. And the energy now, energy is minus mu 0, a summation over r sr dot h, okay, plus 1/2 summation over r prime j r. Let's write it down here. It's not plus, it's minus 1/2 summation over r prime j of r minus r prime s r dot s r prime. This is the total energy, and it depends on the different states of all the different SR and SR primes. Now, instead of using the full expression, I'm using this expression over here. So my energy, now remember, the whole goal is somehow to reach a sum of independent something that can be factorized. Okay, so it equals to the first term. Well, it's the same. So let's look just on the second term. So I have 1/2 a summation over r, summation over r prime, j of r minus r prime, and here I have this guy over here. Minus m squared plus m as sr prime plus sr multiplied by m, bad mark. I'll separate this into 3 double sums. So I have 1/2 a summation over r prime of j r minus r prime multiplied by minus m squared. I have 1/2 summation over r prime j of r minus r prime multiplied by m sr. And I have 1/2 summation over r prime, thank you, of j of r minus r prime sr m. What is this guy? I can take it out. So I have minus m squared divided by 2, a summation over r prime, j of r minus r prime. And here, the not so natural term, I'm saying this is a constant. The summation over r primes, of r minus r primes, it's some specific constant, which is, well, how this guy decays over distances. And I'm saying that this is independent of r, and it's just j tilde. So this guy, just j tilde. If my system is large enough, and for example, I don't care about specific r's, this summation will always produce me a specific constant, which is independent of r. So I have m squared minus, I have 2, and I have a summation over r of j tilde. What is this summation? It's just the number of particles that I have inside my system. So it is minus m squared divided by 2, or, you know what? Let's leave it like this. The idea again that I can sum over all the different interactions without sr prime, and it produces me a constant which is independent of r. Okay, what happens over here? So I can take m out, okay, and I can switch the order of the summation. So I have m divided by 2, a summation of r prime, a sr prime, and I have here a summation over r, j, r minus r prime. Now, due to the fact that j depends on the absolute value, r minus r prime, doesn't matter if I sum over r prime or I sum over r. This is again j tilde. So this is m divided by 2, a summation over r, sr prime, j tilde. R, thank you. R prime, this R prime, this R prime. Thank you. Okay, what about the last term? It's exactly the same as this, right? So it is m divided by 2, a summation over r, sr, a summation over r prime, j over r minus r prime, absolute value, so it's equals to m divided by 2, a summation over r, SR, the same J tilde. Now the last term, not the most important, but the last term is to say, well, this guy, when I sum over all the different r's, I sum over all the different positions of all the different particles, it's a lattice, remember it's a lattice, so it is just minus m squared divided by 2 J tilde multiplied by n. Out of all of those guys, what do I have? I have just m, so I sum them up. So I have m. Does it matter if I sum over r prime or I sum over r?
No.
Absolutely no, because I cover all the different particles. So it is just m multiplied by r of SR J tilde. Okay, so notice something interesting. The energy, now, the total energy is E equals, so I have the first part, which is minus mu 0 summation of r SR vector dot H vector, okay, and I have minus this guy, but minus this guy, this is this guy, and now I know which is, this is plus m squared divided by 2 J tilde multiplied by n, and it's minus m summation of r SR J tilde. Are we happy? We almost are happy. Why are we happy? Well, this is a constant. This is fine. But this is just summation over different SRs. This is just a summation over different SRs, right? So, what can I say next? I can say the following.
But Stas, you can just collapse this, the right term to m squared J tilde. N.
This,
Yes.
I can collapse it where?
To m squared J tilde n.
No.
Yes, because sum of r SR is n
No, it's not.
m.
No, it's not.
Why not?
Because
M is-
SR can be different values.
But m is the average of spin, the average spin.
But SR is not.
But the sum of SR is the number of particles.
No, it's not. That's the average, and this is it's not an average. If I average it, it will become m, but it's not average.
Yes,
And
it's
fluctuate.
m times the average.
No. So SR summation R over R. The average equals to n multiplied by m. The average is important. I don't have an average over here. Right? Okay, so let's write it down in following fashion. Have m squared divided by 2 multiplied by J tilde multiplied by n. I can collapse those two terms over here. Okay? And what I can collapse them to, so I write it in the following way. So it is minus mu 0 h minus m plus m J tilde. And notice what is this m? M appeared due to the multiplication of m and SR. So I can write it down as m vector, and all of this dot a summation over r SR vector. So this is a constant term, and this is a sum over different SRs. So if m equals to 0, I have only the external field mu 0h. Okay? But if m is not equals to 0, I have an additional field. So let us write it down again. E equals to m squared divided by 2 j tilde n minus mu 0 h plus j tilde, which is a scalar, m multiplied by a summation over r SR vector. And here is a dot. So if I won't have this term, and then this is a constant, nobody really cares about the constant, right? So it's a constant. And I have this term over here. Okay? So without the m, what is this? It's the interactions-free Ising model. So the only thing that this mean field approach have done, it's have created an effective field. I can call it effective field. I don't know what this m is. I have absolutely no idea what this m is, but this is an effective field. So I have a free, what the mean field approach eventually tells us, okay, so you have something, you have interactions, but when you forget about the fluctuations around the average value, you take only the first order, not the second order, the energy becomes just a summation over independent values of the different spins multiplied not by the real external field, but the effective field where you have also J and M. Okay? We know how to solve free Ising model. All right? This is effective field plus interactions free Ising model. So I know how to solve it. Right? So let's write down the partition function again. Z equals to a summation over all states e to the power minus beta, the energy. Okay? So it is a summation over all states. So what do you have inside? We have e to the power minus beta, and the energy is this guy now. So it is m squared divided by 2 j tilde n plus, oh, I'm sorry, this is plus, this is minus mu 0 h plus j tilde m dot a summation over r SR. Another parenthesis. Okay. This guy is a constant, so I can take it out. So I have e to the power minus beta m squared divided by 2 j tilde n. I can take out of all the summations, it's independent of the different states of the system. And here I have a summation over all states e to the power beta mu 0 h plus j without tilde m dot a summation over r SR vector. This is a free Ising model, and we solved it already. Free, interactions free, interactions free Ising model. So what's the partition function? Z equals to this part stays the same, e to the power minus beta m squared divided by 2 j tilde n. This guy, we already know it, it's 2 hyperbolic cosine. Now previously it was just mu 0 h, right? But now we have an effective stuff. So it is mu 0 h plus j tilde m beta, and that's it, right? The power of n. This power is important. We succeeded. We still have 20 something minutes left. Hooray! So we have succeeded. We made an approximation. We don't know how exact this approximation is, but at least we have a result. What's the problem now with this result?
We still need to calculate m.
We don't know what m is. So this guy over here, what is m? Okay, so we can calculate out of this the magnetic moments, etc., 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 right? But we don't know what m is. Remember, the magnetic moment now, the average magnetic moment, was what? Mu 0 multiplied by n, hyperbolic tangents of what? Of whatever stands inside. Of mu 0 h plus j tilde m multiplied by beta. And again, we don't know what this m is. The problem with this approach, you plug inside a quantity that you don't know what it is, you use it as if m is something, right? And then you get a result. What is m? This is the real question. Because for example, if m is 0, if m is exactly 0, you'll get nothing, right? If m is exactly 0, you get the interactions free. But when is m not 0, maybe something will happen. Okay? So how to find m? Any ideas how to find m?
You divide large m by n, and then you solve the implicit equation.
You don't know what this is. You don't know what this is, so you have an equations with two unknowns. How you solve it?
No, we know that m divided by a large average m divided by n is equal to small
Okay.
m. And
Yeah,
then
you can do that. You can do that. But there is a much more interesting approach. Okay? And this approach is due to Landau. So the idea of Landau is as follows. This is the beginning of something that's Landau approach. Theory. The idea of Landau is just, well, this is m multiplied by n. Because if the average value of the spin is m, the total magnetization is just m divided by n, and somehow you can solve this equation. But Landau described something different. Landau said, let's continue. Let's continue a little bit further with this. How we continue? Well, let's write the free energy. F is equals to minus 1 over beta log of z. Right? So it equals to, if you take a log of this guy, so minus 1 over beta, a logarithm of e to the power minus beta m squared divided by 2 j tilde n multiplied by 2 hyperbolic cosine of mu 0 h plus j tilde m beta to the power of n. Okay. Let's work with this guy. So what do you obtain? You obtain that f equals to a log of this part is just, so we have minus 1 over beta, and here we have a logarithm of what? Of minus beta m squared divided by 2 j tilde n, and we have minus, right, or plus n, a logarithm of 2 cosine of what? Of mu 0 h plus j tilde multiplied by beta.
J tilde n.
J tilde m. Thank you. Now you have n and n over here. So you have f divided by n. Let's call it small f. It's like a free energy per particle equals to beta cancels out. So I have m squared divided by 2 j tilde. And here you have minus 1 over beta, a log of this monster. 2 hyperbolic cosine of mu 0 h plus j tilde m beta cross it.
With an n outside now?
And it's cancelled.
Ah,
Okay, so we haven't reached anything. You still have m. Maybe the previous idea of solving this guy is better. But Landau had a fantastic idea. The idea of Landau is as follows. So what m should we choose? What is m? So we either can solve this equation, but then, well, maybe it won't work for anything else. But there should be a more general physical principle how to choose m. And the idea of Landau is as follows. So this is f for any m, right? I know that the system eventually will choose a specific m on its own, right? Somehow the system can sample different m's, and eventually it will choose an m on its own. What is the m that it's going to choose?
Extra.
It's external. Minimum.
Minimal value. Minimal value. Okay? The system should choose m such that the free energy is minimal. The physical system chooses m such that the free energy is minimal. You remember we started all this class about all this variational principle. This is the variational principle at its best, right? You have different realizations of the system with different m's. How to choose a specific realization? You choose the minimal value. This is the principle of classical statistical physics, classical thermodynamics, and quantum. It's a little bit different, right? But you choose one m for which this guy have to be minimal. Okay? So what should we do? We should take the derivative of this guy and see. This is the first time that this principle, Landau, that was applied to statistical physics, and all this variational principle developed later on. And this was a crucial turning point on how we observe thermodynamics, how we observe statistical physics, etc., etc., etc. Because eventually, and field theory of statistical physics, eventually you only need to write down something that looks like the free energy and find its minimum. That's always works. It works in classical analytical mechanics. It works for quantum transition from quantum mechanics to classical mechanics, and it works for statistical physics. You have to write down a variational principle and work it out. That's it. Okay, so let's work a little bit over here. So we take df to dm and we assign it to be 0, exactly 0. So what happens? You have to take d to dm of this not so nice guy, m divided by 2 j tilde minus 1 over beta, a logarithm. M squared, thank you. Log of 2 hyperbolic cosines. And now let's work with h equals 0 because it's easier. Otherwise, I have all those terms over here. Okay? And this is the important part, right? When h equals 0. So hyperbolic cosine of j tilde m beta, we call the parentheses, right? So what we have? We have m j tilde minus 1 over beta. So it's a log of something. It is 1 over 2 hyperbolic cosine of j tilde m beta. Now we have to take the inner derivative. What is the inner derivative of 2 cosine? 2 sine.
J beta sine.
2 hyperbolic sine of j tilde m beta. And all of this multiplied by what? By j tilde beta. And all of this equals to 0. Okay? So what we obtain? We obtain that m equals to hyperbolic tangents of j tilde m beta. You could say, Stas, you can obtain this from this magnetization equation. Yes, I can, but this principle is much, much wider, right? Okay, so here we have a single equation for m. How you solve it? You can't, right? You cannot really solve this. But you can plot the different solutions. So you take a plot and you plot on this as a function of m. First you plot m. It's very easy. It's just a straight line. Yes?
You prefer to do a transformation so the constants appear on the left side?
No, it's fine like that. What constants? Those?
Yes.
No, I like it. I like it here. I like it. Really. I can actually do the following. Can delete it. But no, I like it. I like it like this. Absolutely. Okay, so what happens? So this is m. This is a straight line. So it's a graphical solution. Now, what happens to the hyperbolic tangents? We know that it's 0 at 0. So when m equals 0, the hyperbolic tangents equals exactly 0. Now, for large m positive or negative, there are two types of behaviors. One type of behavior is that it goes like this. Right? And then there is only one solution, m equals to 0. Okay. But there is another type of solution. Another type of solution will be plot as a function of m, this m over here. Okay. And it looks like this. Okay. And another type of solution will be So you have minus m star plus m star and m equals 0. Okay, so m equals 0, m equals m star, and m equals minus m star. When this solution happens, and when this case happens, the only thing that matters is the derivative of the hyperbolic tangents at 0, right? So what is the derivative of the hyperbolic tangents at 0 as a function of m? If the derivative is smaller than 1, right? If the derivative of the hyperbolic tangents here is smaller than 1, you have only one crossing point, m equals 0. If the derivative of the hyperbolic tangents is larger than 1, you will have 2 additional crossing points. Okay? You will have 2 additional crossing points, and therefore you have 3 different solutions. Okay. What is the derivative of hyperbolic tangents at 0? d to dm of hyperbolic tangents of j tilde m beta at m equals 0. So you take the derivative, you set m equals to 0, and you obtain what? J tilde beta. Okay. So what we obtain? This happens when j tilde beta equals smaller than 1. This happens when j tilde beta is larger than 1. Alright? So you have 2 different solutions. And you can say, Stas, but what is minima and what is maxima? What actually happens? You have to go and check. And here, m equals 0, f is maximal. F is minimal. You go over here, you'll get, oh, f is maximal. And here, f is minimal. And here, f is minimal. If you plot now, f as a function of m, you get the following behavior. When j tilde b is smaller than 1, you get something that looks like a parabola. Okay. When you plot something which is where I should plot it. When you plot f of m as a function of m for j tilde beta larger than 1, you're getting something that looks like this. So this is m equals 0, this is m star, and this is m minus m star. So what happens? When j beta is smaller than 1, the system always chooses this point, and this is m equals 0. M equals 0 means that the average spin is 0 and there is no magnetization. But when j beta tilde is larger than 1, well, this is not a stable point. This is maximal. The system will choose either m star or minus m star. So what will happen as a function of the temperature? Because you see the transition from this behavior to this behavior happens when? When J beta equals exactly to 1, or J tilde, or J tilde multiplied by 1 over K Boltzmann T equals to 1, or J tilde divided by K Boltzmann equals to T. Exactly this T, and I can call it as the critical T, I have a transition from the average magnetization, magnetic spin is 0. I cross to this point, so here T is smaller than Tc, here T is larger than Tc. When I'm at the region when the temperature is smaller than Tc, I have two additional solutions and there is a net magnetization. Which one I will choose? M star or minus M star? I don't know. It will depend probably on the history. It will probably depend on the initial conditions. So let us plot the average magnetization from this Landau principle. The average magnetization, we know it is N multiplied by the small number m that we have as a function of temperature. For high enough temperatures, the free energy looks like this. So the system always chooses m equals 0. There is no other solutions. So the average magnetization is exactly 0. We reach this specific point when J tilde beta equals exactly to 1. Something peculiar happens over there, okay? But as we cross this point, the system can choose two solutions, either m star or minus m star, okay? What will happen, it will go either up, if it chooses m star, or either down. Exactly this point. How exactly it will choose minus m star or plus m star? As I told you, it depends on the on the initial conditions. So what exactly do we have over here? We have a transition. We have a transition from zero magnetization to non-zero magnetization, global. This is a spontaneous symmetry breaking. And why it occurs? It occurs due to the energy of the system. Okay? So I can say, well, there are interactions and interactions are doing something, etc., but it's still not clear what the interactions are doing. I don't know. There's still the same interactions. I just lowered the temperature, right? But when you plot the free energy, you see that the free energy is either something like this or either something like that. Okay? And here, there are absolutely no other choice for the system but to take the minimal value, and it's always m equals to 0. And for low enough temperatures, the free energy, the energy of the system, have a double minima. And at m equals 0, it's maximal. So this principle tells you, oh, choose minus m star or m star. How exactly the interactions working, I don't really know. The only thing that I know that effectively the energy is either like this or either like that. Yes?
But why the system cannot choose any rotation on the right?
A, is it stable?
Not
Exactly. That's it. That's the point. That's the point. It's not stable. So even if I'll put my system in this specific position, small thermal fluctuations will always drive it either to the left or to the right. It's not a stable point. Moreover, we know that the system has to choose a minimal value. Yes?
But if we return to what we started with dividing to small regions.
Yes.
Now, every small region can select an M on its an M on its own. Like it's all of them. It's like
flipping a coin,
Okay,
M star or minus M star.
okay.
So on average,
No. M star is the same A star. What we assumed, M is the same M for any given spin. Okay, this is what we assumed. Now, this thing over here, the Landau theory, it's always called afterwards the Ginzburg-Landau theory, and how you plot those effective free energies and what you can get out of them. It's the starting point already for the advanced course on classical statistical mechanics. Anyone who is interested, welcome next year because I'm going to teach it over there. The class is over. Thank you all. תודה רבה.
תודה רבה, סטאס. תודה רבה.
סטאס, אז לא עשינו שכנים קרובים למודלייזינג?
הסכימה, לא, אתה לא תצליח לעשות את זה.
לא, כי בתרגול עשינו שכנים קרובים.
ואיך אתה מחשב את ה-J טילדה? J, R, minus R פריים, סכימה על R. אני פשוט אמרתי לך שזה J טילדה, אוקיי? עכשיו, איך אני מסכם? אתה אומר, ה-J הדבר הזה הוא 1 נניח רק לשכנים קרובים ו0 לכל השאר. זה כל מה שיש בשכנים קרובים. בשיטה של שדה ממוצע. אם זה לא שדה ממוצע, זה וואחד פתרון. כלומר, האיש הראשון שפתר את זה לדו-מימד, לאחד מימד אין שום מערב חזה, אבל האיש הראשון שפתר את זה לדו-מימד, קראו לו לארס אונסאגר, הוא קיבל פרס נובל עבור משהו אחר. וזה פתרון שנמשך 48 עמודים. זה מאוד מאוד קשה. ולדעת מימד אין פתרון. קשה. אבל לדו-מימד זה מאוד מאוד קשה. יש פתרון אנליטי, מדויק, רק עבור המקרה של H שווה ל-0. ול-H לא שווה ל-0, גם לדו-מימד אין פתרון מדויק. שכנים קרובים או לא שכנים קרובים. אבל רעיונית אנחנו בדיוק מבינים בדיוק מה שקורה, זה תיאוריה שנקראת רנורמליזיישן. שהיא פותחה בתחילת שנות ה-80. אבל מדויק, אייזן אתה לא יודע לפתור במקרים מאוד מסוימים.
מה אני עושה עם זה?
אתה מבין עכשיו למה אני מוצרת לך מעבר פאזה, יש לך מעבר פאזה.
כן, אבל לא יודע לחשב כלום.
מה אתה יודע לחשב? הנה, חישבת.
אבל לא יודע לחשב את J.
בטח שתתן לי את J, תסכם על כולם וקבל את J טילדה.
זה הספין הממוצע של חלקי.
איך מודדים את J?
מה?
איך אני מוצא את J?
תבוא
למה J טילדה הוא קבוע? תלוי ב-R?
במערכת מספיק גדולה הוא לא תלוי ב-R. מערכת מאוד קטנה הוא יהיה תלוי ב-R, זה נכון.